we're going to continue with this same example, our ball being thrown up in the air, same position function, negative 16t squared plus 25t plus 15. All right, and we're going to answer the question, how long is the ball in the air? And this is actually not a question that has to do with derivatives at all. This is just talking about the amount of time that it takes the ball to complete its trajectory, which is based solely on this position function. So let's think about what this position function looks like. Negative 16t squared, we know from our pre-calculus days that that's a downward opening parabola. So I'm just going to make a rough sketch here of a downward opening parabola. Okay, we're talking about time, which we represent as a positive number, so we'll be on the positive time axis here. And we'll have our distance, our feet on the vertical axis, and it's a downward opening parabola with a y-intercept of a positive 15. So maybe something like this. And it makes sense that this graph would have this kind of position function if we know over time, the height of the ball is going to go up, gravity is going to start pulling it down, and eventually it's going to hit the ground. Now, when you hit the ground, right, so let's think about that phrase, hit the ground. That's also known as your height above the ground being 0. Okay, so this is going to be translated mathematically into our position being equal to 0. All right, setting our y coordinate equal to 0. That's going to be this spot on the time axis. It's also going to be this spot over here where time is negative. We're going to ignore that one because we know it won't make sense in context. All right, but we're essentially just finding what we normally think of as x-intercepts, in this case, the t-intercepts of this position function. So I'm going to take the whole function, negative 16t squared plus 25t plus 15, and set it equal to 0. All right, and I am not going to try to factor that. That's a quadratic equation, and we're going to use the quadratic formula to solve this. All right, so t equal to negative b plus or minus square root b squared minus 4ac all over 2a. If you didn't have a high school teacher that tortured you into memorizing that, that would be a good one to put on your cheat sheet for the exam. All right, so my a is going to be negative 16. B is going to be 25, and C will be 15. So we'll just plug into this and ask the calculator to evaluate for us. All right, so like we expected, we got a negative t-intercept. It's over on the left. That one is meaningless. We're not using time travel. We're not going back in time. So the one we're interested in is that 2.0254. All right, so that's going to be our answer. How long is the ball in the air? It takes it 2.0254 seconds. That's our time unit to finish its trajectory and hit the ground. Of course, the position function kind of implies that the ball continues going down below the surface of the Earth, but we know that that just doesn't make sense in context. Next question is, what is the velocity of the ball as it hits the ground? So we know that right the moment after it hits the ground, its velocity is going to be 0 because it's going to hit the ground. It's going to have no velocity, but we're talking about the impact velocity. So what's the velocity like right at the instant it hits the ground? So again, remember that our derivatives, our instantaneous velocities, have that speedometer strapped to the ball, and then we hit the pause button and we look at that velocity right at the moment that it hits the ground and say, what is the velocity with which it's striking the ground? All right, so we know that the way we calculate that is with our velocity function. So we're going to have our velocity function, which we figured out in the last video, was negative 32t plus 25, just the derivative of our position function. And then what is the velocity of the ball as it hits the ground? We just want to find the velocity when it hits the ground. So when it hits the ground, in the last question we solved for that, and we got t is equal to 2.0254. All we need to do is figure out the velocity of this object, this ball, at 2.0254 seconds. So we're just going to plug that time that we solved for in part C into the velocity function. So negative 32 times 2.0254 plus 25. We'll just ask the calculator to do that. And I'm getting negative 39.8. We'll round that off to one decimal place. All right, and we know that's a velocity that's going to be in feet per second. And it makes sense that we're going to have a negative velocity because you're going to hit the ground as you're at a downward trajectory. Downward means negative velocity. One more question to go and we're done with this ball flying through the air. All right, same ball, same position function. Now we're asked for, when does the ball reach its maximum height? All right, so let's think again about this position function. So I had it kind of sketched out on the last slide. And so we had our downward opening parabola, and we know that it hits the ground a little after 2 seconds. And we're trying to figure out, when does the ball reach its maximum height? So they're asking a when question, which means they're looking for a value on that time axis, on the t-axis. And they're looking for, when does the ball reach its maximum height? So its maximum height is about right here, whatever this value is. We want to know, when does the ball reach that maximum height? So we're looking for the t coordinate that belongs to this maximum point here. All right, so the way we're going to do this is kind of tricky using the velocity function. So remember, the velocity is the derivative of the position function, but let's think more about in terms of a tangent line. So think about this trajectory here. Whenever you're at that maximum spot, your tangent line is going to be completely horizontal, right? So when we're at the max height, our tangent line is horizontal. And a horizontal line has zero slope. Okay, so this is going to be where we have a zero slope. Since it's a tangent line, that means we're going to have a zero derivative. All right, so maximum height for us mathematically is going to translate into, where's the velocity, or when is the velocity equal to 0? And this should kind of make sense. Remember that on the way up, the ball has a positive velocity. On the way down, it has a negative velocity. So the velocity must change from positive to negative by passing through the number 0. So at that brief instantaneous moment of time, when it's just sort of suspended in air, about to turn around and fall, it's got a 0 velocity. So we're going to take our velocity function. Remember, velocity was equal to negative 32t plus 25. And we're going to set that equal to 0. And that's a simple linear equation we can solve. I'm going to subtract 25 from both sides. And then we'll divide both sides by negative 32. So t is going to be negative 25 divided by negative 32. Again, we'll ask our calculator to do that. Negative 25 divided by negative 32. We get a positive 0.78125. And again, that's a time value. It's seconds. And that's the precise instant, that pause button moment, where we would need to hit pause and we would see the ball sitting at its maximum height above the ground.